So if we take a look at this image right here, showing you a connection or a synapse between two neurons, we know that an electrical impulse, when it runs from the dendrites to the cell body, we refer to it as a graded potential. So you're going to have a graded potential running down right here. If it's strong enough, it's going to trigger an action potential, which is going to run down the axon until we hit the axon terminals. So if we're going to zoom in right here, here is the axon terminal, and here is the cell body of another neuron. So you have a stimulus or an action potential running down. As we said, that's going to trigger the vesicles to release the neurotransmitters, which are going to be released in the synaptic cleft. Once those neurotransmitters bind to the receptors, that's going to trigger channels to open up, sodium channels to be more precise, and sodium is going to start entering into the cell. Why is sodium entering into the cell? Because the sodium is going to be moving down its concentration gradient, and so since we have more sodium outside of the cell, the sodium is going to be moving from outside to the inside of the cell. Now, as the sodium enters into the cell, that's going to cause the inside of the cell to depolarize. And as the depolarization, as you can see with the arrows, the depolarization is spreading, its strength actually starts to degrade. And the reason why the strength of that graded potential is actually wearing off as that graded potential starts moving down the cell body is because usually on the surface or on the membrane of the cell body, there are leaky channels that cause those positive charged ions to actually start leaking out. And so as those positive charged ions leak out of the cell, that depolarization signal is going to start decreasing. So you can see right here closer to that area where we had the first kind of trigger, the stimulus, the strength of the graded potential or its amplitude is pretty high. As that graded potential, that nerve impulse starts moving down the cell body, you notice that its amplitude starts to decrease and its strength is basically decreasing. And that's because those leaky channels are forcing those positive charges to move outside. Graded potentials, their strength vary depending on the initial stimulus. The stronger the stimulus, the stronger the graded potential will be. The weaker the stimulus, the weaker that graded potential will become. Now, graded potentials, they only travel short distances. They only travel down the dendrites into the cell body. Once it moves down the axon, remember, it's not called graded potential anymore. We refer to it as action potential. And we said that the graded potential, graded potential loses its strength as it moves down the cell body. Now, for an action potential to be triggered, that graded potential must maintain its strength, especially when it hits that region known as the trigger zone. If the graded potential is pretty weak by the time it reaches the trigger zone, no action potential will be triggered. Now, we know that inside of the cell, the resting membrane potential is around -70 millivolts. So if there is a stimulus that triggered a graded potential, and sodium channels start to open, where sodium ions start to enter into the cell will start depolarizing. So as you can see right here, the shift is taking place, and we are shifting to becoming less negative. Now there is a limit right here where we refer to it as the threshold, which is around negative 55 millivolts. We're gonna explain in just a minute why that threshold is pretty important. But as you can see right here, as the graded potential is running down the cell body, notice how the strength of the arrows are starting to wear off. And so if we go back to this graph, you notice that it was starting pretty strong right here, but you can see that the strength is starting to decrease. That strength of the graded potential is decreasing. Now, if the strength of the graded potential continues to decrease and it becomes lower than that threshold known as negative 55 by the time it reached the trigger zone, then that means the strength of that graded potential is so weak that an action potential is not going to take place. So that threshold needs to be maintained, that negative 55. If it's not maintained, then the signal wears off and the graded potential just dies. The stronger the stimulus, the stronger the graded potential starts off. And so one more time, if a graded potential is triggered, the cell is going to depolarize. But notice how here it's the depolarization wave is much stronger compared to that depolarization wave right here on that image. And that's because that initial stimulus was much higher. Now, the stronger that initial wave of depolarization, the better chance of that graded potential maintaining its strength by the time it reaches that trigger zone. And so one more time, you notice that the graded potential starts losing its strength as it moves down the cell body. But notice by the time right here it reached that trigger zone, it was able to maintain that threshold. And so if it reaches the threshold right at negative 55, or it's actually still a bit if it's a bit higher than negative 55, that means that it is strong enough and an action potential is going to be triggered. So we refer to this right here as a supra-threshold graded potential because it was able to, that stimulus was pretty strong enough at that starting point, and the graded potential was able to maintain its strength, and it was able to still, its strength was able to be a bit higher to that threshold, and so an action potential will result. It doesn't always have to be higher than the threshold, by the way. If the wave is touching that negative 55, that's still going to be strong enough to trigger an action potential. But if the strength is below the threshold, not even at negative 55, that's weak and no action potential will take place. Okay, so the graded potential, as we said, must reach that trigger zone, depolarizing the membrane to the threshold of negative 55 millivolts. Once it reaches that trigger zone and it hits that negative 55, an action potential is going to be triggered. So as we see right here with the graph, we start off, as we said, at negative 70 millivolts. We must reach the negative 55 millivolts. So right here, this part is showing you how a graded potential took place and how that graded potential was able to maintain its strength and it hits that negative 55 millivolts. Once a graded potential hits a negative 55 millivolts, an action potential is going to be triggered. Now, what's going to happen during an action potential? During an action potential, as that depolarization wave is now going to move down an axon, a bunch of voltage-gated sodium channels will go ahead and open. And when those voltage-gated sodium channels open, the sodium is going to start rushing inside of the cell, depolarizing the cell even more. So notice how the wave, that depolarization wave, peaks, and the cell is going to keep depolarizing until we hit a positive 30 millivolts, and we refer to that as the rising phase. So that rising phase is due to a bunch of sodium ions entering from outside to the inside of the cell, and it's going to keep depolarizing until we hit the positive 30 millivolts. By the time we hit that positive 30 millivolts, what's going to happen to those sodium channels? Those sodium channels are going to close. So no more sodium is going to be entering into the cell. So the sodium channels are going to close up here. And what's going to happen is another set of channels will go ahead and open. And those are going to be the potassium channels. So the potassium channels are going to open. Now remember how we said we have more potassium inside compared to outside? And so once those potassium channels open, potassium is actually going to start leaving the cell. Now potassium are positively charged ions, and so if you have a bunch of potassium ions leaving the cell, what happens to the wave is that it's going to start going down, because that membrane potential is now going to start becoming more negative inside of the cell, because you have all of these potassium leaving the cell. So potassium leaves the cell, causing that membrane potential to start becoming less positive. So we are, as you can see, the graph is starting to go down. That membrane potential is going down. And you notice that the membrane potential is basically going back to that negative 70 state. So what's happening is that we are starting to repolarize. Okay, so we are starting to repolarize, going back to that negative 70 millivolts. But notice how it doesn't stop at negative 70. It's actually hyperpolarizing. It's becoming even more negative. That's because the potassium channels don't close right away. The potassium channels keep open. They stay open for a while. And so a lot of potassium leaves the cell. So the more potassium leaves the cell, the more the membrane potential will actually start to hyperpolarize, and it gets really close to like around negative 90 millivolts. Then what happens is the potassium channels are going to finally close. And once the potassium channels, they finally close, no more potassium is going to leave the cell. So you will notice that the membrane potential starts to repolarize and starts to go back to that negative 70 millivolts. So these are the steps that take place during an action potential. So you must hit the threshold first. Once the threshold is hit, an action potential is triggered. Sodium channels open up. Sodium starts rushing inside of the cell, depolarizing the cell to around positive 30. Once you hit positive 30, sodium channels close, potassium channels open, potassium starts rushing out of the cell. and potassium keeps rushing out of the cell to the point that the cell hyperpolarizes. Then potassium channels close and the membrane potential repolarizes, going back to -70 millivolts. And that action potential basically is going to, those steps are going to keep taking place all the way down the axon until we hit that axon terminal. If we look at this image right here and we zoom in on this region, you see the axon hillock or the trigger zone right here, and here is the axon. For an action potential to run down an axon, we have to first make sure that that graded potential has maintained its strength or has maintained that threshold of -55 millivolts. Once the graded potential maintains that -55, an action potential is going to be triggered and it's going to move down the axon. Now, once an action potential is initiated, a bunch of sodium voltage-gated channels will open, and sodium is going to start rushing down into the axon, depolarizing the axon. Now, it's not one action potential that's going to run down the whole entire axon. You're actually going to have several action potentials running down an axon. Now, action potentials, we refer to them as all or none, meaning that once you've initiated an action potential is going to take place and it's going to run down the axon until it reaches the axon terminals. It's all or none. It's not going to stop midway and it's not going to go backwards, and it will move only in one direction. Now, why all or none? Because if the graded potential is not strong enough, then an action potential is not even going to take place. But once an action potential does get initiated, it will move in one direction to the axon terminals. Now, why can an action potential, why can it not go backwards and move in an opposite direction back to the cell body? Well, because as an action potential moves down an axon, the reason why it's not going to be able to go backwards, because as the depolarization wave is moving forward, the sodium channels, remember how we said by the time it hits the +30, the sodium channels will close. And so once the sodium channels close and potassium channels open, that region right here is going to start repolarizing. And so you cannot have another action potential running in an area that just got repolarized, because the sodium channels are closed and everything is going back to normal or going back to that resting membrane potential. So the action potential only moves in one direction, which is towards the axon terminals. The image that we previously looked at was showing an action potential running down an axon. That axon was not myelinated, meaning that it was not covered by a myelin sheath. This image right here is going to show us how an action potential runs down an axon. The only difference is that this axon is myelinated. So these represented by the yellow regions right here, those are the myelin sheath. The myelin sheath is going to act as an insulator, where it basically insulates and protects that axon. And having a myelin sheath causes the action potentials to actually run faster down that axon. Now, why does the myelin sheath allows the action potential to be actually conducted faster? And we refer to it as the saltatory conduction. That's because when an action potential runs down a myelinated axon, we are going to have that depolarization state taking place. So basically, it's the same steps: the sodium channels opening, the sodium entering, that depolarization wave hits a positive 30, sodium closes, the potassium channels open, repolarizing the cell. So those steps are exactly the same. The only big difference is that where do you have those sodium channels? In an unmyelinated axon, you have sodium channels throughout the whole entire axon. So you have sodium channels opening throughout the whole entire axon. In a myelinated axon, you only have the sodium channels in these regions right here, in the regions that are not myelinated, which we refer to as the nodes of Ranvier. So you only have sodium channels only in the regions known as the nodes of Ranvier. Now, so as a depolarization wave passes down an axon and the sodium channels open up and the sodium starts to enter, that's going to make the inside of the axon more positive. And those positive charges are going to start moving down the axon. Now, having sodium channels only at the nodes of Ranvier makes the impulse go faster because you're going to be skipping this whole entire region where you don't have to go through the opening and closing of those sodium channels. And so that makes the impulse run faster because the impulse is now running down the axon and it's skipping this whole entire area, and so it's jumping, and that's why they call it the saltatory conduction, because the action potential, think of it as jumping from one node to another node. And you might wonder, well, how come those positive charges, when they're running down the axon, how come they're not leaking out and causing that action potential to lose its strength? The reason why those positive charges are not going to be leaking out, because there is that myelin sheath acting as an insulator. And so you have the myelin sheath that acts as an insulator, preventing those positive charges from leaking out. And now the action potential is going to be jumping from one node to another node because that's where you have the sodium channels. And so with the myelin sheath, the message or the nerve impulse is going to run way faster compared to not having a myelin sheath. Now, if the myelin sheath starts to degrade, that's going to be pretty bad because those positive charges are actually going to start leaking. And why is that bad? Because if the positive charges are leaked, then the action potential loses its strength and the action potential signal will die. A disorder where individuals start losing their myelin sheath is multiple sclerosis. So with multiple sclerosis, the myelin sheath all of a sudden starts to degrade, and the action potentials are going to start losing their strength. And so individuals that have multiple sclerosis will start suffering from not being able to conduct a lot of activities, and their movement is going to start slowing down because the action potentials are losing their strength.